Welcome to the E-Pathshala lecture series on computer science for postgraduate students. So, we are learning the course computer graphics and visualization. So, we have successfully completed 4 modules in this course, and today in this session we are going to look into the 5th module, which talks about the basic 2D transformations. So, let us have a recap of what we have learnt already. So, we had some introduction, some fundamentals, some definitions and so on. Followed by that, we have learnt about the output primitives. So, we started with the basic line. So, line drawing algorithms like DDA and Bressenheim. Then we proceeded further towards circle drawing algorithm, and later now we are in the session where we will be learning here today basic 2D transformations. Okay. So, in graphics we have to understand that every object is represented as a graphic. Any shape is a graphic, as we understood that from the beginning initial sessions. So, a transformation here is nothing but a change in any attribute of the shape or the object. So, a transformation is a change in attribute. So, here attribute here for an object or a shape here means that for example, take a line. A line has got attributes like its position, its length, its color, its style and so on and so forth. So, similarly, any other object like say take a triangle. A triangle has got attributes like say its position, its size, its maybe orientation and so on. So, what we mean here by transformation is a change in any of the attributes of the shapes or the graphic objects. So, let us get into the course, we will get into the session in detail. So, today we are here to learn the concepts on translation, rotation, scaling, the 3 fundamental transformations. We call these 3, the translation, the rotation and scaling, as fundamental. So, they are very basic, and we also will be learning in this session about usage of a new imaginary coordinate system called homogeneous coordinate system or homogeneous coordinates, and we will exploit the advantage of this coordinate system or coordinates for simplifying all our operations or all our transformations. So, let us look into the 2D geometric transformations. So, whenever we say it is 2D, that means we will be using only 2 dimensions. So, the same thing will be discussed for 3 dimensions in 3D transformations. So, with one more dimension added, the z coordinate added to it. So, fundamentally here in 2D basic geometric transformations, we will be talking about the translation, the rotation and scaling. So, I will explain what each of them mean here. So, translation, rotation and scaling are basic. The other transformations, like you can see in the slide, the other transformations include reflection, shearing, and one more common or most general transformation is transformation between coordinate systems. So, we will learn all this in detail. So, let us start with how to actually perform a transformation, fundamentally the basic ones. Okay. We call the 3 transformations, the translation, rotation, scaling, as basic, because these transformations are the building blocks. That means, for any other transformations like reflection, shear, transformation between coordinate systems, or for whatever be the kind of other complex transformations, they can be represented as a combination of these basic transformations. That means, you can combine these basic transformations in some form to get other advanced transformations. So, that is why we call these things as basic. So, let us start with the first basic transformation, translation. So, translation is one of the important transformations or basic transformations, which is nothing but change in position. Okay. You can here assume that a transformation can be both for geometric transformation or it can be an attribute transformation. That is, as I said, If it is geometric transformation, we deal with size, we deal with position, we deal with orientation and so on. If it is attribute transformation, we will be changing the say color, we will be changing its texture, we will be changing its style and other attributes. So, attributes and geometric variables are different. So, you must be able to appreciate that here we will be dealing only with geometric transformations. So, when we look into the first transformation, that is translation, translation is change in position. So, assume a point in the 2D space, that is imagine p x comma y is a position, is a point. So, it has to be moved to a new location, say p dashed x dashed y dashed. Now, how do we represent this transformation? So, let t be the transformation and we use t to indicate translation. Okay. So, from x to x dashed, x has moved to x dashed and y has moved to y dashed. That means, take the x coordinate, it has moved to a new position x dashed, and the y coordinate has moved to a new position y dashed. So, if you look at the equations here, you can simply represent x dashed as x plus t x and y dashed as y plus t y. So, these t x and t y are nothing but the translational distances, one along the x direction, the other along the y direction. That means, from x to, if you travel along the x axis by t x units, you will reach the x dashed position, and from this position, if you travel along the y axis by t y units, you will be reaching the y dashed position. So, x dashed and y dashed can be represented as x plus t x and y plus t y respectively. So, these are equations in their equation form. So, we can write that in a notation form. So, let p dashed be the point x dashed y dashed representing the point x dashed y dashed, let p be the point representing the position x y, and let t be representing the translational distances t x and t y respectively. So, this notation you should remember that it is actually p plus t, an addition. So, the initial position plus some addition. So, conveniently we can write these equations in matrix representation. So, for our convenient understanding and representation, because when we do our implementation in a program or in say an algorithm, representing these equations in matrix form are more convenient for programmers. So, every equation that we get in graphics will be converted in this particular topic like 2D transformations will be converted into a matrix equivalent, and then we will be performing operations on matrices. So, let us see how the matrix representation of translation is given. So, it is a 2 by 1 matrix, x dashed y dashed is equal to x and y is the P matrix plus the T matrix T x T y. So, it is a 2 by 1 matrix for the x dash y dash, it is a 2 by 1 matrix for P and 2 by 1 for T. So, we will be doing these things similarly for the other transformations like rotation and scaling. So, let us look into what is rotation and how do we perform rotation transformation. See, as I said, a transformation is a change in attributes or a change in some geometric attributes of the shape. So, as I said, as we just understood that translation is change in position, and here rotation is the next transformation, which is nothing but change in orientation. So, what is change in orientation? Orientation is, say you turn, you tilt, you orient yourself with respect to a given fixed position. So, how do you orient yourself is orientation. So, let us look into the scenario here. Let this be the coordinate system x y represented with x y, and let p be the position, which is p x comma y is the position, initial position. Now, this has to be rotated about origin. This point p x comma y has to be rotated about origin, so that it has now moved to another position, say p dashed, x dashed, y dashed. So, our aim is to now find out what are the coordinates x dashed and y dashed in terms of x, y and some more other parameters, and let us see the other parameters in this scenario. Connect the origin with the point. So, we call this with a straight line, we call this the radius vector. Connect the origin with the position p x comma y, we call this the radius vector, or you can give the length as r. Okay. So, obviously, when we are performing rotation, r is going to be constant. So, for whatever be the new position, r is going to be constant because it is simply rotation. So, let the line connecting the origin and the new position p dashed be the same line, that is the same radius, or it is exactly of same length r. Okay. This line is actually any line in connecting any point in space, any line from origin that starts from origin and connects the point in the 2D space is actually called the position vector of that point. So, any point in space when connected with a straight line from the origin is called the position vector of that point. Okay. So, let this line be the position vector of the point, let OP. So, maybe origin and P is the position vector of the point P, and the line connecting the origin and the P dashed is called position vector of the point P dashed. Okay. So, for our further equations and derivations, let us assume that the position vector of the point P makes an angle phi with x axis, and let the position vector of the point p dashed makes an angle phi plus theta with x axis. So, I am again repeating this, let the position vector of the point p make an angle phi with x axis, and the position vector of the point p dashed makes an angle phi plus theta with x axis. So, our interest is in the angle theta, that is theta is the angle of rotation. So, theta is the angle of rotation from p to p dashed is what we are moving. So, let us see how the derivation proceeds, and for the position vector of the point p dashed and the x axis. So, you can take the cosine of the angle phi. So, you can take cos of phi, cos phi is equal to adjacent side by hypotenuse. So, cos phi is nothing but x by r, cos phi is nothing but x by r for the position vector of the point p. So, x is equal to r cos phi. Similarly, take sine of the angle phi for the position vector of the point p. So, sin phi is equal to y by r. So, y is equal to r sin phi. Now, we have got these two equations, keep them aside. Now, let the position vector of the point p. So, as we understood that the position vector of the point p dashed makes an angle phi plus theta with x axis. So, it makes an angle phi plus theta with x axis. So, for the phi plus theta angle, that is for the position vector p dashed, take the cosine of the angle. So, cos of phi plus theta is equal to x dashed by r. So, as we did similarly for the previous position vector. So, it is phi plus theta is the angle, that is the change. So, let cos of phi plus theta is equal to x dashed by r. So, x dashed is equal to r cos phi plus theta. Similarly, y dashed is equal to r sin phi plus theta. So, if you expand say cos of a plus b and similarly sin of a plus b. So, you get the equations expanded like this, x dashed is equal to r cos phi cos theta minus r sin phi sin theta. Similarly, y dashed is equal to r cos phi sin theta plus r sin phi cos theta. So, because sin of a plus b, sin a cos b plus cos a sin b. Okay. So, what is that we are doing is now this r cos phi in the equation is actually computed previously as x, and r sin phi is computed as y. So, replace r cos phi with x and r sin phi with y in the equations. So, what do you get finally is x dashed is equal to x cos theta minus y sin theta, and y dashed is equal to x sin theta plus y cos theta. These are the two important final equations which you will have to remember. So, as I just mentioned, we will be representing all equations as matrix equivalents because of programming simplicity, or we can use them in programs than to use equations. So, it will be easier to do matrix operations. So, let us rewrite these equations in their matrix equivalent form. So, you can easily like take this conversion from equation to matrix form. X dashed y dashed is equal to cos theta minus sin theta cos theta and x y. So, this matrix cos theta minus sin theta cos theta is called the rotation matrix, and theta is the angle of rotation, that is important. So, theta is the angle of rotation, phi is eliminated in the equations. So, theta is the important angle of rotation. So, notation, if you write a notation representation for this, it gives us p dashed is equal to r of theta into p. There is a multiplication, that is what you should notice. P dashed is equal to r of theta into p. In the case of previous transformation, that is translation, there was addition. Okay. Now, as we know from conventions that rotation in counterclockwise directions are positive and rotations in clockwise directions are considered negative. So, whenever you have to perform negative rotations, that is clockwise rotations, you change the theta to minus theta. Okay. So, that is how the conventions are. Let us move to the third basic transformation, the scaling. Okay. As translation is change in position, rotation is change in orientation, and scaling is change in size. Okay. Here scaling change in size here means it can be upscaling or it can be downscaling. That means, it can be increase in size or it can be decrease in size. So, scaling is one is a peculiar transformation where it involves both change in size as well as change in position. So, you will observe that maybe from the equations you will be able to appreciate that. Scaling involves inherently two transformations, one is change in size, the other one is change in position. So, as you see here in the diagram there, imagine you have an initial position, say p x comma y. Okay, the blue colored position or blue circle, it is a blue filled circle, circle filled in blue, and the circle filled in red is the new position. Okay. Let this be the initial position and this be the new position. Imagine a shape. Okay. For scaling, you cannot just assume a point, because scaling a point is meaningless, is not it. For scaling, you have to imagine a shape or an area. Okay. So, then you can appreciate that okay, something is increasing in size or its size is increasing or decreasing. So, for that sake we have chosen here a rectangle shape, and the position is p x comma y. Now, imagine this rectangle, it has to be scaled. Now, if you look at the equations here, it is simply scaling simply is multiplication. Scaling simply is multiplication. That means, imagine you are holding a shape. Okay. If you want to upscale it, that is if you want to increase the size, what is that you would do? You can stretch the object or the shape along x direction, and you can also hold the shape and stretch it along y direction. The whole object gets scaled. So, if you want to squeeze the object, that is scale down the object, what is that you do is squeeze it along x direction and squeeze it along y direction. So, on both directions if you squeeze it, the object or the shape becomes smaller in size. So, that is the effect of scaling. So, that means, we will be increasing the size along x direction and increasing the size along y direction. On a whole, the object size increases. So, it is basically multiplication. So, as you see here in the equations, x dashed is equal to x multiplied with s x, y dashed is equal to y multiplied with s y, where s x and s y are scaling factors along the x and y directions respectively. These are constant numbers. So, the higher the values of s x and s y, the higher is the scaling. So, if the scaling factors are generally it is 1 is the default size or the default scaling factor, that is if you substitute s x is equal to s y is equal to 1, what happens is we call that no scaling. Okay. We because x dashed is x, y dashed is y, there is no scaling. Okay. If the value of scaling factors is beyond 1, that is maybe higher values or lower values, it leads to a scale up or scale down respectively. Okay. So, as you see here, this is the initial rectangle. When it is scaled up, the new rectangle, that is the scaled rectangle, has gone to this position. It has become bigger in size and has also moved to a new position. That is what you should observe. So, it has become bigger in size, not only it has become bigger in size, but also has moved to a new position. But when you scale it down, what happened is the size has reduced, the size of the object is now reduced, but and now it has moved to a new position which is towards origin. That is what you should observe. The scaled up object has moved away from origin, the scaled down object has moved close towards origin. So, that means as you reduce the scaling factors by say lesser than 1 and say 0.5, 0.2, what happens is when you multiply x with 0 and y with 0. So, assume scaling factors are 0, 0, what happens? X dash is equal to 0, y dash is equal to 0. That means the object is not there, it is just a null. So, it is at origin. So, these equations are represented in their matrix equivalent form, as you can see on the matrix equivalent representation. X dashed y dashed is equal to S x 0 0 S y into x y. So, the notation you can represent this in notation equivalent, because for simplicity, for making this more what is called a representation, better representation, you can use this notation. P dashed is equal to S, where S is the scaling matrix, S x 0 0 S y, it is a 2 by 2 scaling matrix. The S x and S y are the non-zero values and P is the point. So, the scaling matrix is now multiplied with the position. So, in translation we have got an addition, in rotation we have got a multiplication of the rotation matrix with the point, and in the scaling transformation we have got the scaling matrix multiplied with the point. So, let us see how the scaling factors affect the shape of the object. When S x is equal to S y is equal to 1, it is no scaling. As I said, when the scaling factors are 1, there is no scaling. So, the object remains as it is. When S x is equal to S y, it is called uniform scaling. S x not equal to S y, non-uniform scaling, and when the values of both S x and S y are greater than 1, it leads to a scaled up object or a increased size object of a bigger size, and S x S y less than 1, it is called downscaling. Okay. Let us have a glance at all the 3 transformations, the basic ones, and at a glance if you see all the 3, you would notice that there is an addition for translation in the notation. You can see in the notation there is an addition for translation, T is the translation matrix, there is a multiplication for the rotation transformation, there is a multiplication for the scaling transformation as well in the when you summarize all the 3 basic transformations. So, now the important point to observe is all these transformations are the basic ones are assumed to be performed with respect to origin. That means, origin is our reference point with respect to which we did everything. So, for example, take a rotation. We have performed rotation of some position P with respect to origin, and so we have moved to a new position P dashed. That means, we are rotating about origin. Okay. So, imagine if you have to rotate or if you have to perform rotation about some other point in space or some other object in space or some other location in space, what would happen to these equations? So, how the equations are different in that case. So, for the time being, let us assume that if we perform the transformations like rotation and scaling in particular with respect to any other point in space other than origin. So, again let me repeat that, if we have to perform the transformations like scaling, rotation, not with respect to origin, but with respect to some other fixed point in space or some other pivot point in space. What happens actually to these equations is, we will do the derivation later. For the time being, just assume that we will get an extra matrix. So, this question mark in the towards the right of the matrices, there are two elements. There is an addition, there is a 2 by 1 matrix whose values are to be, whose elements are to be derived. So, here for the scaling matrix also there is one addition of another matrix of size 2 by 1 whose elements are to be derived later. So, for the time being you assume that an additional matrix will be there when we perform scaling or rotation with respect to some other point in space other than origin. So, now the notations, you can look at the notations. P dashed is equal to P plus T is the translation matrix, and it is an addition, simple addition. But for rotation we get an additional matrix, let us call that MR. MR indicates an additional matrix of size 2 by 1 when we perform rotation with respect to any other fixed point, any other pivot point. Similarly, for the scaling transformation we get an additional matrix MS, which is a 2 by 1 matrix at 2 rows and 1 column, whose elements are to be derived, and we will when we derive that we will know what the elements are. So, now we will be converting all the three, that is, if you look at all the three, there is a pattern that we can evolve from all the three basic transformations. What is that pattern? So, let us see this pattern. The first translation P dashed is equal to, you can write P plus T as I into P plus T, where I is the identity matrix of size 2 by 1. So, it will not be changing any values there. So, we can conveniently put this P as I into P plus T. So, there is one matrix multiplication and one addition. For rotation, there is already one rotation matrix R of theta into P and plus MR. For scaling, P dashed is equal to S into P plus MS. So, in all the three, we have brought all the three into one common format, or into one common form, one multiplication and one addition, one multiplication and one addition. So, what is its what is the advantage of representing these in one common notation or form? What happens actually is, if you do a series of transformations, like for example, in animations, in cartoons, in what is called, whatever you see in animation movies, what actually happens is a series of transformations are performed in succession. That means, if you imagine a Tom and Jerry like cartoon, or if you imagine maybe the Donald Duck, maybe the Kung Fu Panda, whatever the animation movies that involve lot of changes, many changes in a short time happen. So, for example, there is a translation. The characters like say take for example, the Tom and Jerry case. Tom runs quicker, there is a translation. Take for example, the popular animation shows like Tom and Jerry, like maybe many other cartoons that you see on television. So, the animation involves too many changes in a short time. That means, if you look at Tom and Jerry like in the cartoon, what happens is always Tom is behind the Jerry. So, Tom moves at a faster pace, at a quick, it suddenly changes its position, it changes its size. For example, when it quickly proceeds to grab the Jerry suddenly escapes and it hits a big wall like object, let us assume, and its shape gets deformed, and again it retains its shape back in just no time, and again it starts running. So, see, imagine so many changes happen in a short time, in a quick succession. So, change in shape, change in size, change in orientation, it turns, twists, it bends. So, so many things happen in succession. So, when more than one transformation is performed on the same object in succession, what happens is, when we use these representations like say one multiplication, one addition, one multiplication, one addition. Let us see what happens in the case of an example when you have to perform a translation, a rotation, a scaling and a translation in succession. Imagine you have to perform a translation, a rotation, a scaling and a translation. There are 4 transformations to be performed in succession on the same object. So, first you performed a translation. What happens is you will be using the matrix identity into P. The P is the initial coordinates. You have got one matrix multiplication, then store the result somewhere and then add it to the translation matrix. So, P there is a multiplication and one addition. So, you did these many things, multiplication, addition. So, 2 matrix operations and then store the result somewhere in the P dashed and then use that as input for the next transformation, that is rotation, and multiply that with the initial coordinates and add that extra matrix and then store the result. So, again there is one multiplication, one addition, as you remember that in the equations that we have seen in the previous slide, there is one multiplication, one addition and then store the result, an intermediate result in some other variable, and then use that result again for the next transformation as input and then multiply and add another matrix. So, if you have to do all this for 4 transformations like translation, rotation, scaling, transformation, you will be doing 8 matrix operations, and over that and above that you will be actually storing the intermediate result also. So, you will be storing the intermediate result and as well you will be doing 8 matrix operations, 4 multiplications and 4 additions. So, imagine so much you will have to do. So, if you have to be more quicker in the operations, you will not be doing this, because in general in a typical animation there are too many operations that are performed in succession. So, we cannot afford to go with these kinds of equations. So, we will have to devise a new way to actually reduce the number of matrix operations, thereby time and what is called the speed. We get more speed and the time in which the operations are performed is much more, it gives a better result in a short time. What actually happens is we will be introducing a new coordinate system called the homogeneous coordinate system, or we can call them as homogeneous coordinates. It is an imaginary coordinate system. So, our general 2D coordinate system is called Cartesian coordinate system. So, we are now looking for an imaginary 3-dimensional coordinate system called homogeneous coordinate system, and the coordinates are now called as homogeneous coordinates, and now all our transformations will be representing them in homogeneous as homogeneous transformation matrices. So, what is the advantage of using this homogeneous coordinates is, we will see that in the next slide, but here let us see how do we represent, how do we convert between Cartesian coordinate system and homogeneous coordinate system. So, a Cartesian coordinate system has got 2 coordinates x and y. A homogeneous coordinate system is, as I said, it is an imaginary 3-dimensional coordinate system which has got coordinates x h, y h and h. So, where x h is the x coordinate of the homogeneous coordinate system, y h y coordinate of the homogeneous coordinate system, and h is the homogeneous coordinate. Now, how do we perform conversion between Cartesian and homogeneous and vice versa? So, how is that done is, so see the equations here, x is equal to x in Cartesian is equal to x in homogeneous divided by the homogeneous coordinate, and y is equal to y h by h. So, now when h is chosen as 1, when this homogeneous coordinate is chosen as 1, homogeneous coordinate is something like, it is an imaginary dimension, as I said, it is a number, you can choose any number, any real number for that sake. If you choose h to be 1, then x is x h, y is y h. So, x becomes equal to x h, y becomes y h. So, if you see this conversion now, the x and y of the Cartesian coordinate system, when they are converted to homogeneous coordinate system, they become x, y and an additional 1. Okay. Now, what is the advantage of converting Cartesian from coordinates from Cartesian coordinate system to homogeneous coordinates is, the advantages as you can see here in the slide. When we when we do the conversions, you will know, we will appreciate that better. So, let us see the advantages of homogeneous coordinate system. whenever you have a complex problem to solve, the general idea is to convert the current data in the data into some other domain and then perform all our calculations in that domain or in that system, and then get back to the original system or the original domain. That is the general way to most common way to solve complex problems. Again, let me repeat, whenever we have a complex problem to solve, we go into a different domain altogether, where data is represented in a much simpler manner and operations are also much simpler. So, we perform all our operations in that domain and again take our result back into the original domain. It is similar to converting data from time domain to frequency domain and frequency domain to time domain and so on. So, whenever we have to perform complex operations, we go into a different domain which simplifies all the operations. Okay. So, the advantage of using homogeneous coordinates is will be evident by when we solve some problems, but for the time being you just take this, that is given the initial coordinates, straight away we get the final coordinate. That means, imagine a series of transformations like translation, rotation, scaling, translation are performed in succession. So, if you give the input coordinates, straight away get the final coordinates, you do not have to store them, store the intermediate result, or you do not have to perform multiplication, addition, and it is just simply multiplication. Okay. That is the first statement. A series of transformations can be represented as matrix multiplication. So, T R S T, if you have to perform, you just multiply them, T into R into S into T. So, it is as simple as that in homogeneous system, and given the initial coordinates, get straight away the final coordinates by compositing these series of transformations. And finally, the number of matrix operations are reduced to just exactly half. So, it is just multiplication and no additions. So, storage of intermediate results is also not required. So, these are the many advantages due to which we represent all our data in homogeneous coordinate system. So, we will maybe do this in the next session. We will try to say how the homogeneous coordinate system helps to simplify our matrix operations and representation of data. So, from Cartesian to homogeneous, how to represent transformations. We will take it up in the next session. So, what we have learnt in this session is the fundamental transformations like geometric transformations I mean. So, translation, rotation and scaling. Translation is change in position, rotation is change in orientation, and scaling is change in size. And also we have seen a bit into how to convert Cartesian coordinates into homogeneous coordinates, and what are the advantages of this representation in homogeneous coordinates. So, thank you.